Okay, yeah. So good afternoon, everyone. Thank you so much for coming for this seminar. Sorry about the delay. Just that computer just took forever to just log in. So today I will be presenting on a machine, Brushless Doubly-Fed Reluctance machine. So we have been working on this machine. Me and Professor Arijit Banerjee, we have been working on this machine for the last 2 years. So this project was given to us by NASA. They had asked us to investigate this machine for turboelectric propulsion systems. Unfortunately, the funding was only till 1 year, but so the funding got over last year only. But we thought about we will keep investigating for this machine. We'll try to improve the design of this machine and try to see how we can improve the torque in this machine. So commercial airlines, just like any other means of transport, they also release carbon dioxide into the atmosphere. If you look at the pie chart over here, the commercial airlines produces some amount of carbon dioxide, which is much less than that of automobiles and the personal trucks, and more than the rail and buses. But however, given the potential to apply alternative fuel technologies to the land-based transport, the percentage of commercial airlines in the coming 10 to 30 years is going to increase beyond this number. And if we zoom into this commercial airlines, what we find out is that the single aisle and twin aisle systems, which carry more than 100 passengers, they are responsible for more than 90% of those emissions. So overall, commercial aircraft produces around 1,500 billion pounds of carbon dioxide every year. And as the demand for air travel keeps increasing, this number is going to increase as well. So the National Academy of Sciences, Engineering and Medicine, they came up with 4 high-level approaches in order to reduce these emissions. Going forward with turboelectric propulsion systems was one of the approaches. So what happens in these systems is these systems employ gas turbines to drive the electric generators, and the electric generators power the various motors which drive. So each motor drives a propeller fan. The thrust of the propeller fan can be controlled by varying the speed of these motors. So, and as we know that in the next 10 to 30 years, the battery technology is not going to be improved that much. Therefore, turboelectric propulsion systems are considered to be the only viable option for the next 30 years. So the target for us was to look for, the target was to investigate that what should be the best motor drive architecture for driving one of these fans. So far, most prospective architectures looked at single port machines. So in these machines, you require a power converter, which has to be fully rated. What happens is, why do you need this power converter is to decouple the generator speed from the motor speed. And since these machines are rated for megawatts of power, these converters have to be rated for megawatt as well. These large amount of power, so the ability to capture this large amount of power through these converters make these converters massive, complex, and bulky. And a study by NASA actually indicated that the weight of power electronics is actually exceeding the weight of machines. So the objective was to look at a motor drive architecture in which you can reduce the size of power electronics as well. And that's where the Doubly-Fed machines come into play. So in these machines, what happens is in the Doubly-Fed induction machine, you have a stator winding, you have a rotor winding. Since the rotor only carries a slip percentage of power, the power converter which is connected to this rotor winding only has to carry a slip percentage of power as well. So in order to, for a specific application and for limited speed range applications, the converter has to be rated for just fractional amount of power. The problem with this architecture is you have to access the rotating windings with the use of brushes and slip rings, which increases a lot of maintenance, reduces reliability of the system, and which we do not want in a system like electric aircrafts. So what we want is a brushless Doubly-Fed machine. The idea is to go from brushes to having no brushes. So that's where the brushless Doubly-Fed machines come into play. So what we have is there are 2 stationary windings over here. There are no windings on the rotor. The winding on the rotor has been moved onto the winding on the stator. Again, one of the stator is connected to your grid directly, whereas another stator is connected to the grid via this power converter. So in these applications as well, the power converter is fractionally rated, and also you remove all the brushes and slip rings as well. Let's look at the cross-sectional area of this machine to better understand like how this machine looks like. So this is the drive architecture of a brushless Doubly-Fed reluctance machine. Over here, you can see that this is your primary stator or one of the stators, which is directly connected to your AC grid or your three-phase supply. Your secondary stator, which is another stator winding, is connected to the grid via this power converter. Both these stationary windings are of different poles in these machines. You don't want a transformer type coupling between two stationary windings. That's why the poles on these two stationary windings have to be different. Now, if there are two fields which are of different poles, then how do they generate torque? It's because of this reluctance rotor over here. This reluctance rotor couples both of the stationary windings through a process known as flux modulation. You can see that you are feeding two windings over here. That's why this machine is doubly fed. The rotor is reluctance, and there are no slip rings. That's why the machine is brushless. If you combine all these three terms, you get a brushless doubly fed reluctance machine. We actually investigated this machine a lot, like last year. What we found out with this machine has very poor torque, like much lower torque density as compared to single port machines. So on one hand, you are gaining on the power electronics side. On the other hand, you are losing on the machine side. So your machine, for getting the same torque, your machine size is much larger as compared to single port machines. So the idea, first of all, is to see that why this machine has poor torque density, and secondly, how can we improve upon that? So in order to do that, let's look at the fundamental component, which is the air gap flux density. So if you have a uniform air gap machine, let's say a PM machine or an induction machine, and let's consider an example of a 4-pole stationary winding with a 4-pole rotor. If you look at the air gap flux density, if you look at the various harmonics, what you will find out is that there is only one component, and that is your fundamental air gap flux density. Whereas in a BDFRM, that's not the case. As I mentioned earlier, the poles on your primary stator, your secondary stator, and rotor, all three have to be different. So what happens is, if you excite your 4-pole stator with, let's say, example of 6-pole rotor, which looks like this, a reluctance rotor, what happens, as I mentioned earlier, through the process of flux modulation, your flux density splits into various other harmonics. So this is your fundamental component, and you get a lot of different harmonics. In order to produce torque, what you will ideally want is to have a secondary stator having 2-pole pair. Since you cannot have 4-pole pair on a secondary, because primary and secondary, they have to be of different pole pairs. In order to produce torque, what we can have? A stator which has 2-pole pairs. The other harmonics you can see are not contributing to torque at all, and they just contribute to leakage. That's why these machines fundamentally are poor in terms of torque density and power factor, because they don't utilize all the components for the production of torque. So what we can do is, we can have a tertiary stator winding in the same stator slots, which are of 8-pole pair. If we have another stationary winding which can interact with this harmonic, we will be able to generate some amount of extra torque out of the machine, since we will be utilizing this component for the production of torque as well. So how do we do that? Is by the introduction of another winding. So you have a primary stator, again directly connected to your 3-phase AC source. You have 2 windings which are controllable. One is secondary stator, another is tertiary stator winding. Both have to be controlled. So there are 2 inverters over here, drive and converter 1 and drive and converter 2. So right now what we are having is, by the introduction of this tertiary stator winding, what we are expecting is we will be able to increase some amount of torque at the expense of including some additional power electronics. So again, there is like a trade-off over here about getting extra power and including some amount of extra power electronics as well. So how much torque do we expect out of this by the addition of this machine? So when we used analytical model, what we found out is, by the addition of a tertiary winding, we can generate 25% extra torque if we have equal amp turn excitation on all 3 stator windings. So we created a FEA model. We excited all three windings. What we find out is, with respect to the conventional BDFRM, which has just 2 windings, we got an additional 15% torque using FEA. This number, however, does not match with our analytical prediction of 25%. It's actually much lower than 25%. So again, we had to go back and look at the analytical model, that why that analytical model is failing when we are adding this tertiary winding. So you can see over here, Right now, what I'm showing over here, I'm just exciting my tertiary winding, and I'm looking at the air gap flux density waveforms at various air gap angles. What you can see is that the analytical model prediction and the FEA, they do not match very well. You can see from the Fourier transform of that flux density as well. Some components are higher, some are lower, so the model which we were using for a primary and secondary seems to be failing for this sort of winding. So why is that? Why is that happening? So before that, first let's look at the model which I was using for calculation and how can we improve upon that model. So over here, this diagram actually shows the stator and rotor. What I have done is, so this is again a BDFRM only. I have just cut open the machine and laid it out flat. So this is your stator over here, and this is your reluctance rotor. There are various barriers which are the air gap over here. Actually, a lot of you are taking 598. We discussed this reluctance rotor in today's class as well. So there are flux guides. So ideally, if you assume iron to be infinitely impermeable, what will happen is that if some flux starts to flow along this iron duct, it should ideally come out of this iron duct as well. That's what our assumption was for all analytical models built so far. But what happens is when we excite our tertiary winding, so these are the flux lines what we see by exciting tertiary winding. What we observe over here is that doesn't seem to hold true. Over here, you can see that a lot of flux lines are actually crossing these air gap barriers. And what we found out is that these flux lines flow as if they see a uniform air gap. They do not see a reluctance rotor, but they see a uniform air gap just like in a PM machine or an induction machine. And why is that happening? It's because of the presence of these iron ribs. So there are some iron ribs present over here and at the back end of these rotor ducts. Why those iron ribs are present? In order to provide some mechanical strength to this rotor. Secondly, iron is not infinitely permeable. So it may happen that the flux lines may cross these air gaps, and that's why the analytical model is failing for this tertiary stator. So we account for this uniform air gap along with the modulated air gap, and we build a semi-analytical model based on these FEA observations. What we found out is that now the FEA results match very well with the model built so far, and you can see both the Fourier transform as well as the waveforms for the flux density match really well. So with this model, so far what we have done is we have included a tertiary winding. We expected a torque increase of 25%, but we got an increase of 15%, which is justifiable based on the assumptions which we took. Now the next goal was to see whether we can increase the torque further. So far the one assumption which I was using is that I'm exciting all the windings with same amount of current, but that's not necessarily true. So the next target is to see if we can create an optimization problem formulation such that in order to find out that what's the proper excitation on all these three stator windings in order to produce maximum amount of torque under current and flux density constraints. So over here, the first problem you see is that we are trying to maximize the torque. The design variables are the three stator winding currents. So we need to find out, okay, what should be the current on primary, what should be the current on secondary, and what should be the current on tertiary. So I'm trying to maximize my torque under my current density as well as my flux density constants. You don't need to see what all there is. But ideally what I'm trying to do over here is that the current density places a limit on, okay, how much current I can put for IP as well as IS as well as IT. So it places an upper limit on those three stator winding currents. The flux density constants are a bit weird for this machine. These machines, the flux density is not sinusoidal at all. There are a lot of harmonics, right? So what we try to find out is we need to satisfy the flux density constraint for all air gap angles. That's a very challenging task. In order to avoid that, what we do is we try to find out some critical air gap angles. If we can find some critical air gap angle, what that means is if we can satisfy the flux density constraints for those critical air gap angle, that means that the flux density constants are satisfied for all the air gap angles. We don't need to do it for all angles from 0 to 2 pi. So we did that. We used an optimization solver in MATLAB by finding all these critical phi's and satisfying all these constraints. And the next slide actually shows the results what we obtained with a conventional BDFRM as well as a BDFRM with an additional stator winding. So what we observe is that you can actually get 26% more torque as compared to a conventional BDFRM by properly exciting all three stator windings. The disadvantage, as you can see, that a torque ripple has increased from this blue waveform to this red waveform. And this was actually expected. Why? This was expected because right now I'm coupling my primary and secondary and primary and tertiary. And unfortunately, there is some unwanted coupling happening between secondary stator and tertiary stator, which contributes to this torque ripple. So obviously we're getting more torque ripple. Since I'm introducing more current in my stator slots, I'm increasing my current density, which leads to more copper losses. Also, with the introduction of another stator winding, I'm introducing a lot more flux density harmonics as well, which leads to more core losses. And that's why the losses also increase from 37 to 60 kilowatt. And efficiency drops from 96.2% to 97%. So there are some advantages and there are some disadvantages. Over here, the optimization process was to maximize torque. We can actually have some other optimization variables as well in order to minimize torque ripple. Torque ripple also depends a lot on how you have designed your rotor. So far, we have not looked into how should we design a rotor. So that would be our next target. How do we design rotor to minimize the torque ripple? We can have efficiency in the optimization problem formulation so that we are maximizing the torque as well as efficiency as well. So some of the key takeaways from this project so far is that, first of all, yes, this machine is definitely an attractive option for this turboelectric propulsion systems because you reduce the size of power electronics. Unfortunately, you lose on the machine side. So we are trying to utilize other flux density harmonics to increase the torque. We saw that by introducing another winding, we can increase torque by up to 26%. There are further challenges to this. Now we have 3 stator windings in one slot. That won't be very easy to design. It will be really hard to design 3 stator windings in just one particular slot. Also, we have 2 inverters over here. You can see now there are 2 stator windings connected to your inverter. So the control is not going to be that easy as well. So these are the further challenges which we will try to look into as well. Yeah, there you go. Thank you. Yeah, questions? Andrew.
Are your critical angles that you talked about geometry or excitation?
So they are a factor of excitation, definitely. So this shows the curve for one particular excitation. But what will happen is that there are a lot of discontinuities because of rotor segments right now. But these peaks will change based on these excitations. So whatever the design variables are, these peaks will change. That's why these critical air gap angles are calculated in terms of these design variables only.
Okay, so each time you go
through a process, these are find out. So these critical angles are find out based on what the current value of this is, and then the constraints are satisfied.
And then for your optimization,
yeah,
have you done any sort of like sensitivity to see how flat this is, or like you ran to an optimal set of points, right?
Yeah.
But if you add any sort of noise in the
sure,
or something like that, do you arrive at pretty much the same point?
Like,
I'm curious how.
Do you think that like?
What does your function look like? Does it flatten out and you've got a pretty wide range where it's plus or minus a few %, or is it very peaky?
So on the x-axis, on the y-axis you are saying the torque, on the x-axis you are saying these design variables, right?
Yeah.
And other design variables. I did not.
There's more dimensions there.
Sure. I mean, yeah, there will be like this will be like a 4D figure. Yeah, but I have not looked into that. I'm hoping that the MATLAB gave me a global optimization value. But I'm guessing it may not be true. You're absolutely right. If I do a sensitivity analysis by changing just one variable, it may happen that I'm actually getting more torque or less torque out of that. So I can look into that.
Well,
that's a good point.
It'll also be interesting, like once you start looking at
sure,
minimizing your torque ripple.
Yeah.
Right. Like then you can do a multi-objective optimization.
Sure.
Right up front.
Definitely.
You'll also probably see how kind of flat
this is. Okay. Yeah. Sure. I will look into that. Yeah. The problem is like the constraints are not very good to solve. Yeah. They are. The constraints are the most difficult part of this optimization process. So it's not very easy to the eyes to look into this process. But yeah, I can do that, at least do the sensitivity analysis on this. Yeah.
It looks like you have a good base to work on. Right?
Sure.
You have this part.
Yeah.
And adding another objective.
Objective should be okay. Okay. Yeah. Sure. Thanks. Yeah, Shalom.
What's your power factor for this overall system?
The power factor of the primary at rated condition was around 0.8. Secondary, it varies. Like at rated condition, since So my secondary stator is connected through that converter right now. So it depends at what speed you're operating at. So at synchronous speed, what happens is, so if you operate at synchronous speed, let me show you this one. So by synchronous speed, I have not put all those things over here. So at synchronous speed, what happens is this machine is connected to AC, so this is directly connected to this one, but this starts to behave like a DC at one particular rate, at one particular synchronous speed, and that's the rated speed for me right now. So this is like a DC, so the power factor does not mean anything over here. So it behaves like a synchronous machine. So this is your stator and this is your rotor windings. But it's around 0.8 at rated condition for your primary stator.
Yeah, that's better than I thought, because this machine is like so from one point of view, it's like a synchronous reluctance machine, right?
Yes.
The rotor. And then it also utilizes the flux modulation effects. It looks like a vernier type of machine.
Yeah.
And both of this type of machines
have poor power factor. Yes, that is correct.
So you have a 0.8 power factor.
Yes, and by introduction of tertiary winding, we can actually improve the power factor even further, because now we are contributing to less leakage and more utilization of harmonics. Yeah, thanks. Yeah, Fu.
So what is the rating for the power current connect to the tertiary?
So we have not derived the DQ model for the tertiary stator so far. So we need to derive the DQ model and then see the size of the power converter. Yeah, that will be the next step. But yeah, we have not done that so far. Deriving the DQ model for this, it's not going to be that straightforward. So yeah, we'll see. Oh yes, Jonathan.
So I like the work that you're doing. This all looks really good. I just want to play devil's advocate for a second. If you go
Sure.
back to your last slide,
Yeah.
you're talking about your 15 to 20%, but your losses are increasing by almost 100%.
But over here, right?
Going from 37
Yes.
to 60 kilowatts,
Yes.
but your torque's only increasing by 10 to 15%. Does this seem like a viable option, or is this something that you...
But right now the machine, like the output power is around 1.3 megawatts. So we should look in terms of the efficiency, right? So your torque, the increase in torque is around 15%, but if you multiply it with the speed, which is around 10,000 RPM for this case, the losses have only increased from 37 to 60 kilowatt, whereas you're getting around, I think 400 or around 300 or 400 kilowatts of extra power as well.
Okay.
So that seems reasonable. The more important thing is what's the size of power electronics now, what we have added.
Okay.
Is that the amount of extra power which we are getting from power electronics as well? So does that make sense? Because we have increased the machine size now, but we have increased our power electronics now. So what's the point where we say that this is the optimal point?
So Jonathan, to answer briefly, if efficiency goes down, we try to talk about efficiency numbers. If efficiency increases, we talk about losses.
Okay.
That's how we try to highlight things, right?
Okay.
So if efficiency goes down, this is not 97 to 96.2. And if our efficiency goes from 97 to 98, we say, oh, we have reduced our losses by 1%.
All right.
So that's the process.
Okay. All right.
But I agree with you. To be honest with you, this is not a great viable option. Let me be clear with this.
Okay.
But I think what Shivang has found out after all, so this was our initial thought process. And let me take the blame. This was kind of a stupid idea. It was from me. So that I always thought of utilizing more harmonics can be useful. But it apparently turns out it's not so nice. So what Shivang found out while playing with this machine for a long time is that you can get much better torque improvement just with having two windings. So I think for all presentation...
that will be the next question in 590. So you won't see three windings in next seminar.
Three winding is kind of a dead end for us right now.
All right.
So it's like almost, we are not going further with this at this point.
Sounds good. But like I said, I really like the stuff you're doing. I just had that question about
Sure.
that.
But what I really appreciate about Shivang, I'm not praising in front of the entire crowd here, is this is one of those machines where I have no clue how this machine operates.
Mm-hmm.
This is such a complicated machine, it just falls apart all my understanding about machines. So I'm glad that at least he picked up and came up to those pi angles, he shows me those equations. I said, rest of the group brings me equations, I try to derive it myself. This equation, I say, okay, whatever you derive, I don't want to get into this. This is so much a nightmare. Please, it's good that you have done this, but it's a crazy machine to work with. All right.
Right, thank you guys.
Okay, hello everyone. Today I'm going to talk about a distributed and scalable electromechanical actuator for bio-inspired robot. I'd like to thank Professor Banerjee and my colleagues over here. So most of the time, robotic actuators, they use conventional method, which is high-speed DC motors with gear trains. Saying they use high-speed motors and they combine gear trains so that they can get higher torque, but they sacrifice speed over here. And because of that and many other mechanical complexities, they require numerous mechanical parts that causes design complexity. And the motor with gearboxes has challenges in back drivability and compliance issues. So what we came up with is that we went through the animal spines such as cheetah and snake, their spine. So for example, if you look at over there, they are distributed actuation. The red dots saying that it is a downward actuation, and green dots saying it is upward actuation, so that they can act like more agile. They can move more agile method. So for example, in a sheep spine, the vertebrae's range of motion varies between 6 to 10. I mentioned this because I was targeting this range of motion for my each module. So here are the benefits of an active spine. So it controls if we have active spine in a robot, it can control the robot's center of mass into the system that can reduce certain amount of energy for certain walking patterns. So in this paper, it says in a humanoid robot, this is only simulation based, but if it has active spine, it can save up to 26.5% of total energy consumption with same motion. And it can also, because of controlling the center of mass, it can maintain the balance better, and it improves the flexibility, and compared to the rigid torso, we can have more various motions. And of course, it looks more natural. It's getting close to the actual animals. And this is the proposed distributed electromechanical actuator system that I have. I have total 6 modules, and then at the end there's a small I-shaped core to provide flux path. And then each module has power electronics, which has 2 DC-DC converters inside and 2 current sensors inside, and each module has 2 coils. So basically, I excite these 2 coils alternatively because because the force is always attractive, so I don't want to like sacrifice myself while operating the system. So this is the video that I'm gonna run. Before I start the video, this video is with the spring versions, with the spring in the coil holder, so that I can improve my force capability when the air gap is really large. So this is just for where I'm up to now, and then after this slide, I'm gonna talk about the actuator analysis without spring. So how do can you click this? I don't know how to click this. Oh. So there are 2 different motions. This is just left and right full swing, and I'm increasing the speed. And I'm gonna move on to the animal-like spine, like S shape, like a wave. And I also increase the speed in between. Okay, thank you. Okay, let's move on. So this is the system overview. So one link has 2 coils and 2 DC-DC converters inside and 2 current sensors, and controller is external, and that gives the proper the required PWM signals so that I can control current. And each motor has limited rotation, so that cumulatively it has a wider range of motion. So to show the magnetic flux path, is actually my magnetic flux path is actually in 3D because I'm using the joint and the clamp as a part of flux path, and they are all in the same material as the E core. So for example, let's say I excite coil 1 and flux starts from A to B, and from B is actually in 3D. So go through the front and back side of the clamps, and then B to C, B, C, D, E, or N, B, C prime, D prime, E. And then E goes back to F and G, and the G, A and G between here, this is the air gap. So when it is stacked, this is how it is operated. So when, for example, this is the ideal case, when I excite all of the coils over here, they are equally balanced so that they produce same amount of torque, so that they are all balanced over here. And in this case, I excite on the bottom side of the coil for module ABC, so that it can produce clockwise torque. And then D through I put current on the top side coil so that it can produce counterclockwise coils, so it can make A shape. So this is the first calculation based on the magnetic analysis. It is depending on the number of turns and the currents and the air gap, and eventually I'm using the flux density analysis approach for the first calculation. So I went through these design considerations to maximize the specific force for the chosen angular flexibility, because I define specific force as a force divided by mass, and then angular flexibility, I was targeting from 6 to 10 degree because I was comparing to the ship vertebra. So angular flexibility is calculated like this. I'm not gonna went through like all the calculation. So we are in this design step. We are assuming these two models are in parallel. So to begin with, I compared with the flux density. And another variable is that I'm actually varying the A, the core limb width, and D, but I make A and D square shape. A and D seems identical, so the area, the force producing area is same, not the same. It's square shape. So while varying the A, which is limb width, and another constraint that I gave here is 50 millimeter of length and 40 millimeter of height. That number is based on the CMU snake robot. They use some similar volume and similar cross-sectional area. So that was my initial external design constraint. And from there, I varied the leg width size, so that as I increase the leg size, the coil area should be decreased. That's why the flux density is decreasing. And if I have smaller air gap, I'll of course have higher flux density for a given amount of MMF. But I'm limiting the flux density of 1.5 because this is average value, because I don't want to like highly saturate the core. Over here, this compares the specific force versus the limb size. As I increase the limb size, specific force increases, it peaks, but it decreases at the end. It's because of the MMF decreases as I increase the A, and the weight also, total weight decreases because the core material density is less than actually copper weight, because as I increase the A, core material increases, but the copper volume decreases. This is how it's calculated. So this is the specific force graph depending on the air gap and depending on the A. So if I go to the lower air gap, I get high force and high specific force. So the peaking point, the optimized point, is around 9 millimeter for the selection. But at the same time, I don't want to sacrifice my angular flexibility, which I was targeting 6 to 10 degree. So I decided to go for 2 millimeter air gap because 2 millimeter air gap gives me around 9.1 degree of angular flexibility. And another thing is that except for the parallel position, the air gap is not uniform, as you can see over here. So what I did was I divided into many number of surfaces so that I can have n number of air gaps and then n number of reluctance. So from there I calculate the flux density, and then at the end I calculate the sum of the force for each area to calculate the total force over here. So each area has to be divided by n because original area was AC, but it is divided by n and it is summed up to a calculator. So, and this is FEA result, which shows this analytical approach is with this. Actually, this image was motivated me to approach this analysis because each area has different flux density. It's not fair to compare like average flux density over here. So at the end, because this is low air gap distance, it is highly saturated. But as I go inner side, it is not saturated. So this is the comparison between single uniform air gap analytic model versus the distributed air gap with core saturation analytic model. So that if we assume there are uniform air gap, for example, let's say let's pick the outer dimension of the. Let's say this one from this air gap varies from 0 to 4 millimeter. Then it varies from over here matches pretty well because the air gap is large, so relatively it has not much effect on it. But as the air gaps get smaller, in this model I'm assuming air gap is 0, that goes infinite, but which is not true. So distributed air gap analysis matches really well with the FEA simulation. Okay, this is the FEA simulation with multimodal operation. I want to mention this because in this system, flux path is not only stuck in the one module. It can be shared through the whole system, shown as this. So over here, I connected 2 modules and the top module so that I can show this is the shared flux path over the whole system, and I'm exciting only the bottom coils. So to compare with the single module and the 2 modules excitation, so I'm actually plotting the flux density curve over on this surface. For the single module, I get 1.54 Tesla, but for 2 modules, if I excite two coils at the same time, I get higher flux density. This is because over here we are in this single module we are using this reluctance in the core, but in 2 modules we are mostly skipping this module. So we have less reluctance over all the systems so that we can get higher flux density with same current excitation. This is more like effective in smaller air gap because air gap is the most of the reluctance in the system. So if I excite on the other side, this effect is going to be less effective. And this is the experimental setup. I fixed the bottom part so that it doesn't go really crazy. And the controller is external. And I put the 3D printed support in the center of mass onto the system so that I can balance them. This is the spine motions. This is the snapshots of the video we saw. So over here, when it is left swing, I'm exciting 1, 3, 5, 7, 9, and 11 coils. And on the right, it is always on the right side. And in S shape, for example, at this moment, I'm exciting 2, 4, 5, 7, 9, 10. So over here, I'm exciting only 6 coils at the same time. So assuming I'm doing open loop control, very simple control. So even if I increase the speed of the motion, I'm actually exciting only 6 coils at the same time, so energy consumption remains same. That is all. And this is the force measurement. I fixed the air gap to be 2 millimeter, so that it is balanced position, so that I can measure the force easily. So this is the FEA simulation. This is the experiment value. The reason why it has error is that because while I'm operating, it is already magnetized, so it has some stiction inside. So that's why it is a bit below. So thank you, and I'm open to questions.
Thank you for your nice presentation. How did you measure that force?
I used pulley method using the hanging weight. Yeah, because due to the limitation of hanging weight, I only have up to 1.5 kilogram, so I could approach to up to this point. Mm-hmm.
Just out of curiosity, what does your code look like? Is it like
Co-author?
your code?
My code?
Yeah. How are you controlling this? Is this like if statements or?
What do you mean if statement? For the motion,
Yeah.
it is simple open loop control.
Okay.
So in certain sequence.
It's a terrible code.
Yeah.
I run into the same thing. I was just curious, like what you were doing.
I made it that simple way to to show the
At this point,
robotic
it's
motion.
not modular at all. It has to be written in a nice functional form.
Mhm.
But I think the focus right now is more on the actuator design itself. That the control is just the icing on the cake at this point.
Totally. I was just curious.
But it,
Because
it's like
I have
million code lines, like if.
I typically would do the if, but there could be some very interesting ways to do it,
That's gonna be the next word. Yeah.
like as a function of angle.
Yeah. Mhm.
Just my curiosity. So here you are using the magnetic field.
Mhm.
The drawback of using magnetic field is heavy. So is there a way? Is it possible to do the same thing but with electrostatic? You use the capacitor instead of the inductor. Maybe you have to go to 4 or 5 kV voltage, but it will be much lighter.
But first of all, for high voltage aspect, we don't want to put high voltage in the animal like robots because they're around human and people.
The microwave will have 1.5 kV into that microwave voltage.
Okay.
So I mean, is there a need to make it much lighter or more power dense for in this?
Yeah. The next target is gonna be the reducing the weight so that we can increase the specific force. So that's actually a good point, increasing the voltage crazy high.
But can you make it electrostatic? That's what this question is, right?
Yeah, can you make it?
I believe it is crazy. It is complete. No. It is completely different actuator because actually other research groups are doing electrostatic with high voltage actuation. So at this point it's a bit different. A bit.
What you do is you want something to attract on this point or attract on the other point, so you can pull the joint to the left or to the right. So if you have 2 planes of charge and you charge the same polarity, then they're pushing, and charging the opposite polarity that they pulling. So
Is it pushing?
You'd be better off if you had like sheets on top of each other rather than actually closing a gap like that.
yeah, put some insulation in between them.
I actually looked into this a while ago, and it doesn't hold a lot of weight, so you don't see them using anything heavy duty. So you all see those really light, flexible robots. It's just because it can't handle weight.
The electrostatic ones?
Yeah, like electroactive polymers is basically a capacitor with a flexible dielectric. It doesn't work very well for load applications.
But they can create very high forces, right? For their force per unit mass is very high.
Yeah, but it doesn't work well because it's also very slow. Like for a full actuation, I think it's 4 seconds for the motion.
So you're saying the specific force is really high, but it has limited force. It produces limited force, so that it is not desirable for the heavily loaded applications.
It's very slow, and the voltage I've seen were close to 10 kV. We talked to someone in the Massey building. He said it's not very good for what you're trying to do.
Okay, good to know. I'll look into it. Yeah.
You will create an electrostatic actuator?
I'll just look into it to see if we can take advantage of that. Okay, thank you.